Using the fundamental theorem of algebra. Now that we can find rational zeros for a polynomial function, we will look at a theorem that discusses the number of complex zeros of a polynomial function. The fundamental theorem of algebra tells us that every polynomial function has at least one complex zero. This theorem forms the foundation for solving polynomial equations. Suppose f is a polynomial function of degree 4, and f of x is equal to 0. The fundamental theorem of algebra states that there is at least one complex solution. Call it c subscript 1. By the factor theorem, we can write f of x as a product of x minus c subscript 1 and a polynomial quotient. Since x minus c subscript 1 is linear, the polynomial quotient will be of degree 3. Now we apply the fundamental theorem of algebra to the third degree polynomial quotient. It will have at least one complex zero. Call it c subscript 2. So we can write the polynomial quotient as a product of x minus c subscript 2 and a new polynomial quotient of degree 2. We continue to apply the fundamental theorem of algebra until all of the zeros are found. There will be 4 of them, and each one will yield a factor of f of x. The fundamental theorem of algebra states that if f of x is a polynomial of degree n greater than 0, then f of x has at least one complex zero. We can use this theorem to argue that if f of x is a polynomial of degree n greater than 0, and a is a non-zero real number, then f of x has exactly n linear factors. So therefore we're going to use this form. F of x is equal to a times x minus c subscript 1 times x minus c subscript 2 all the way to x minus c subscript n, where these are complex numbers, c1, c2, and c subscript n. Therefore, f of x has n roots if we allow for multiplicities. Now, does every polynomial have at least one imaginary zero? Well, that answer is no, because real numbers are a subset of complex numbers, but not the other way around. A complex number is not necessarily imaginary. Real numbers are also complex numbers.